Video 20 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the interaction picture. As you might know, there are actually several formulations of quantum mechanics. There are at least one more, or two actually, in addition to the Schrödinger formulation as we know it. In the normal Schrödinger picture, we have that the operators are time independent in general, apart from if we have an explicit time dependence in our system, like for example, if we uh, consider a system where there's also an electromagnetic wave present. But in the absence of these kind of explicit time-dependent perturbations, our operators, which we use in the Schrödinger picture, are time independent. The time dependence is in the wave function, and there it is in the form of this time-dependent phase factor. So the Schrödinger picture is a natural choice for the time-independent systems. Another second picture which we want to use here in this book is the so-called interaction or Dirac picture. That is very useful for time-dependent situations, so where we have an Hamiltonian which is time-dependent, and here we have our normal time-independent Hamiltonian, and as I said before, we have then an extra perturbation Hamiltonian describing the interaction of our system with some kind of time-dependent perturbation. Now the wave functions and the operators in this interaction picture, they are obtained by the wave function and the operators in the Schrödinger picture by these unitary transformations, where we multiply the wave function with an exponential operator having here the time-independent Hamiltonian. And correspondingly, the operators are sandwiched with this exponential operator and the exponential operator where we have the complex conjugate of the exponent. They differ now in the form, so you can see that our operators now also are time dependent, and in general, of course, the wave function are also still time dependent. Although the operators and the wave functions are now different than in the Schrödinger picture, you can easily see that expectation values of these operators with these wave functions will give the same result as the expectation values of the operators and wave function in the Schrödinger picture. And the same applies to overlap integrals or norm integrals. And that's actually the only important thing, because all observables are related to expectation values. So and how precisely we formulate the operators and the wave function, that's just mathematics. We already had a similar example before in chapter 2, where we talked about gauge transformation of the vector on scalar potentials, where we also could change the potentials without affecting the value of the fields. Now let's try to understand what this transformation change from the Schrödinger to the interaction picture physically means. Therefore, let's look at the case where our time-dependent perturbation operator actually is 0. So our Hamiltonian is still time independent. And then in this case, the time-dependent wave function in the Schrödinger picture, the time dependence is then, as we know, is just this time-dependent phase factor, where here we have the time-independent wave function, and the time dependence is just in this phase factor. And of course, since that's the energy of this state, and this state is an eigenfunction, I mean, it's one of the stationary states, it's an eigenfunction of the Hamiltonian, we can write this exponential here, exponential operator, instead of with the energy, we can also write it with the Hamiltonian, so it's really an operator. And as we already have discussed, the time dependence is given by this phase factor, also as the word already says, it's just a rotation in the complex plane. Now let's look at the time-dependent wave function in the interaction picture. And as we've seen on the slide before, the wave function in the interaction picture is obtained from the time-dependent wave function in the Schrödinger picture by applying this exponential operator to it. Now if I insert for this special case where h1 is 0, our time-dependent wave function in the Schrödinger picture, which is this one here, then we can see that, of course, those two exponential operators cancel each other. I mean, the product of two is 1, which means our time-dependent wave function in the action picture in this time-independent situation is actually just the time-independent wave function, which means the time dependence, this time-dependent phase factor, which we had in the Schrödinger picture, is now removed in the interaction picture. So the rotation in the complex plane due to our time-independent Hamiltonian is frozen out. One can also say in a different way, and in the interaction picture, we switch to the rotating frame of the time-dependent phase factor from the Schrödinger picture. A very nice analogy describing this situation is a merry-go-round. In the Schrödinger picture, let's exemplify the wave function by one of the horses of the merry-go-round, and we are the observer, and we are standing outside of the merry-go-round. So in the Schrödinger picture, we can see the horses going around in a circle in the complex plane. Now, going to the interaction picture actually means that we're going to step onto the merry-go-round next to the horse. And then when we look at the horse now in the interaction picture, meaning standing on the merry-go-round, the horse doesn't move anymore. It's just standing next to us. So the rotation coming from the unperturbed Hamiltonian is no longer there. And this is very, very useful because when we have a time-dependent situation where we have an external time-dependent field perturbing our system, so we actually have a Hamiltonian, perturbation Hamiltonian, first order perturbation Hamiltonian, then we are not really interested in the time dependence coming from the unperturbed Hamiltonian. We are interested in the time dependence introduced in the system, the extra time dependence introduced in the system by this perturbation Hamiltonian. And in a Schrödinger picture, that's always mixed up with the time dependence coming from zeroth order Hamiltonian, whereas if you go to the interaction picture, we then, because there the time dependence through the unperturbed from the unperturbed Hamiltonian is frozen out, we can only purely see the time dependence introduced in the system by our first order perturbation operator. And therefore in the following chapter we will go to use this interaction or Dirac picture.